я не могу.
Мы можем сейчас найти. Давайте проверим на всякий случай, все ли у нас запланировано.
Кто-нибудь уже записывает?
Что?
Вы знаете, как записывать?
Вот вроде как нажали только что. Я просто не знаю, оно запланировано или нет. Давайте проверим.
Вы как-то уведомляли о том, что вы запланировали трансляцию? Вы как-то уведомляли, чем начали, что в 108 будет трансляция?
Ну, Гоша мне сказал, что будет 108, наверное.
Да, вот говорит, тут говорит, не забудьте включить.
Что?
Говорит, не забудьте включить.
Сейчас посмотрим.
Вот.
Ну что-то запланировано.
Да.
Все, меня видно, меня слышно, я, наверное, там уже минуту как чушь несу. Okay, so let us finally start. First of all, I would like to say that it is time to finally generate some problem sets. So I hope that today or tomorrow I'll send the first problem set for the course. And today we are going to continue our movement towards the prime number theorem, but we will take a slight complex analytic detour, so that today we are going to discuss zeta of s as a function of complex variable. As I have noted before, zeta of s was first considered by Leonard Euler, sorry, and okay, and at first Euler treated zeta of s as a function of real variable, and he was also able to guess the functional equation using some numerical approximations. But then some people realized the connection between zeta function and distribution of primes, and kind of the main contribution was the paper by Bernhard Riemann, published in 1859. Riemann proved that zeta function can be extended to a meromorphic function of complex variable s with only one pole, and he also established a connection between zeros of zeta of s and distribution of primes. This statement about the connection between distribution of primes is also a little bit inaccurate because, as far as I understand, Riemann was not actually interested in estimating the counting function of primes. He was interested in closed formula, kind of. Okay, so what we're going to prove today is the following result. Zeta of s has an analytic continuation to a meromorphic function on complex numbers with only one simple pole at s equals 1. Okay. To do so, let us first prove that Okay, so to remind everyone, zeta of s is of course equal to the sum over all n from 1 to plus infinity, 1 over n to the s. To do so, we first need to discuss some obvious complex analytic properties of zeta of s. So maybe one is some easy stuff. Okay, so first of all, the series for zeta of s defines a holomorphic function in the following region. Real part of s, which is, as you might remember, sigma, greater than 1. Okay? So this statement is that if you take this series and consider it in the half plane of convergence, then you get a holomorphic function. How to prove this statement?
Равномерный предел.
So if you have un holomorphic functions in some region D, and UNs converge to some function U uniformly, then U is also holomorphic. This is easy by, for example, Morera theorem.
Может быть, uniformly это у нас равномерно.
Да, равномерно. So if you have a sequence of functions which converge uniformly to some other function, and all these functions are holomorphic, then the result is also holomorphic. To prove this, you can consider, for example, a given triangle in your.
It's holomorphic in its inner.
Of course, D should be open. If D is open, then you can do this, right?
So something like maybe open and connected.
So this should be a domain, right?
Domain, yeah.
Correct.
Зачем связанность?
Зачем связность? Хороший вопрос.
Если равномерно сходится везде, то и на каждой компоненте сходится равномерно.
Well, I remember that this theorem in complex analysis was given to us with D as a domain. So
Okay,
this
so
is why I said
our domains would be some half planes, so we do not actually care about topology of our D. It's just an example, okay? So to prove this, you just prove that you just note that the integral of your UN over any triangle is equal to 0, right? And by uniform convergence, this converges to the integral of U over the same triangle, right? This means that the integral U dz over any triangle is equal to 0, and then by Morera theorem, U is holomorphic. And that's it. Okay, so how do we prove, how do we relate this to our result? Well, take any epsilon greater than 0, consider the domain sigma greater than 1 plus epsilon, then the following obvious sequence of holomorphic functions converges to zeta of s uniformly, right? Sum of all, say, n greater than n, n to the minus s is bounded by sum over all n, greater than n, n to the minus 1 minus epsilon, which goes to 0 as n goes to infinity. This is due to absolute convergence of our series.
Вопрос.
Ага.
То есть, слева просто у нас частичная сумма.
Yeah, so you take partial sums and then everything converges to what you need. Okay? Nice. So, this is a trivial statement. This is only due to convergence and nothing else. Let us continue. Let us literally continue zeta. Let us extend zeta of s to sigma greater than 0. We already did this, but let us discuss in more details about the convergence to a meromorphic function. Let me remind you that, zeta of s. Assume for now that sigma is greater than 1, then zeta of s is equal to this series, then it is equal to 1 plus integral from 1 to plus infinity u to the minus s d integer part of u. This is equal to 1 plus say integer part of u to the that's not what I wanted to do. This is equal to integral from 1 to plus infinity u to the minus s du minus integral from 1 to plus infinity u to the minus s d fractional part of u, as usual. Then this is equal to 1 plus, what is the value of this integral? Please, someone.
Which one? Just
This one. What?
У меня записано 1 делить на s минус 1.
Конечно. Of course, this integral is equal to, let me write it here, u to the power 1 minus s divided by 1 minus s from 1 to plus infinity. At plus infinity you get 0, at 1 you get 1 over 1 minus s, and then you should take the difference. So this is equal to 1 over s minus 1, and then you get this integral, which I would like to integrate by parts. This is basically my favorite thing to do is with some integral is to integrate by parts. Okay, so what do you get here? Well, the boundary terms are equal to 0 because the integer part, the fractional part of 1 is equal to 0, and at infinity you get you get a decreasing function, and you get 0. So this is equal to 1 plus 1 over s minus 1 plus what?
1 over 1 minus s. Not sure.
No, because you should take the value at plus infinity, then the value at 1, and then subtract 1 from another, right? This would be extremely strange if we get 1 over 1 minus s, because if s is large and positive, we should get something positive here, right? Okay. So this is equal to integral from 1 to plus infinity fractional part of u du to the minus s, which is equal to 1 plus 1 over s minus 1 minus s times integral from 1 to plus infinity u to the minus s minus 1 fractional part of u du, right? Is everything correct here? Yeah, probably so, right?
Сейчас, а мы нигде не потеряли, вот когда интегрируют по частям константы?
Граничные члены,
Да.
я уже объяснил, что здесь дробная часть равна нулю в единице,
А, ну,
бесконечность
да,
по
всё
выбыванию. Okay. So what is this? This stuff is, of course, holomorphic. This is a constant. This is meromorphic, and this is globally meromorphic, right? And this integral converges when? When does this integral converge?
S is bigger than 0.
Real part of s is greater than 0. So this converges absolutely for sigma greater than 0. So this means that this integral is actually holomorphic for real part of s greater than 0. Why is that so?
Because you can just ignore the fraction part. View it as a constant.
Well, why is it holomorphic? We know that it converges, but why is it holomorphic? Well, you can take, for example, any compact subset of this half plane, and then in this compact subset, you can also prove that this is holomorphic, for example, by Morera theorem, right? The same thing. Okay, so what we know now is that zeta of s is meromorphic in the following region. Real part of s greater than 0. And we also know that at s equals 1, we have a pole, right? And nothing else. Correct?
Yep.
Okay. What we are going to do now is instead of continuing this process, actually one can continue this process integrating the fractional part, then doing integration by parts once again, and then continuing this indefinitely. You can prove that zeta is meromorphic in the whole complex plane, but this is a very boring method. So let us instead prove everything by the functional equation. So what is the functional equation for zeta of s? Well, first of all, definition. Gamma of s. Do we have some people in the audience who know what is a gamma function? Please raise your hand if you know what is an Euler gamma function.
Ага, сейчас это интеграл, который x1 минус x. Или нет, сейчас?
У нее есть такой...
Не бета, а гамма.
Oh, is it the only log convex function that satisfies?
Yeah, correct. Okay, so gamma function.
It can be defined like million ways.
Gamma function will be the following: x to s minus 1, e to the minus x, dx. So when you first write down such an integral, it is not immediately obvious why should you care about anything like this, right? So let me give you two obvious, well, one very obvious and one less so motivation. Why should we consider such an integral? First of all, gamma of n plus 1, where n is a natural number, is equal to what? Can you tell me, please?
N factorial.
This is equal to n factorial, and also s gamma s is equal to gamma of s plus 1. Why?
Integration by part.
Due to integration by parts. This is easily proved. For example, integral from 0 to plus infinity x to s minus 1 e to the minus x dx is equal to integral from 0 to plus infinity e to the minus x dx to the s over s. Then you integrate by parts. The boundary terms are 0, and you get 1 over s minus 1 over s, integral from 0 to plus infinity, x to the s, d e to the minus x, which is equal to 1 over s, integral from 0 to plus infinity, x to the s, e to the minus x, dx, which is equal to gamma of s plus 1 over s, right? Okay? Easy computation. So this formula also proves that gamma function can be extended to a meromorphic function in the whole complex plane, right? Correct? Because your integral defines, obviously defines a meromorphic, a holomorphic function for real part of s greater than 0, and then you apply your functional equation repeatedly and get a meromorphic function, right? Okay, and where are the poles of gamma? Correct. Poles are, as usual, simple. And located at s equals minus n. N is natural. So everybody knows that you cannot compute a factorial of a negative integer, right? Gamma function allows you to do everything but computing factorials of negative integers. For example, due to the definition of gamma function, you can actually compute, say, factorial of a half. What is a factorial of 1/2?
Pi over something.
Not exactly. It's a square root of pi. I think divided by 2. Yeah. So factorial of 1/2 is square root of pi divided by 2 by this computation. Okay.
Есть еще факториал числа и.
Of what? Ага. Его можно прям посчитать?
Нельзя, но значение очень странное.
Yeah. Using these formulas, you can, for example, compute an absolute value of a factorial of imaginary unit, and it will be related to hyperbolic sign.
Isn't the theory inside the scope?
What?
The theory isn't why the 2 is not inside the square?
Иначе больше единицы будет. А у нас в нуле в единицы, ну, известно, что она...
So factorial should be do you think half should be inside square root? Well, gamma of 1/2 is equal to square root of pi, right? Then gamma of 3/2 is half of gamma of 1/2, so you get this. Okay, let's continue doing something instead of talking about nothing. Okay, so what is the functional equation for the Riemann zeta function? This will be theorem 2, I think. For any s in complex numbers, we have pi to the minus half, gamma of pi to the minus half of s, gamma of half of s, zeta of s is equal to pi to the minus half of 1 minus s, gamma of half of 1 minus s, zeta of 1 minus s. Okay? So, of course, to prove this identity, one first needs to make sense of both halves of the equation. So, for example, if we only know what is zeta of s, so if we only know what is zeta of s for real part of s greater than 1, then this equation does not make sense at all, right? But if we were able to prove this identity, for example, for real part of s between 0 and 1, then it would make sense, and due to the identity principle, it will also continue to the whole complex plane, right? Okay. What?
You prove it's holomorphic.
So if we know that this function is meromorphic when real part of s is between 0 and 1. And if we prove this identity, then this will be an identity of two meromorphic functions in some open subset of complex numbers, right? And if they coincide on open subset, then they coincide everywhere. Okay. So we only need to prove this for values where we already know what is zeta of s, right? Okay, but first, before proving this, we need to establish some lemmas. Well, I will tell you my favorite proof of this result using modularity of theta function. And during the seminar, Piotr will tell you some other things, some other ways to prove the functional equation. Okay. So we first need a few more things. The first lemma will be as follows. First, I need to remind you what is the Fourier transform. We will use Fourier transform of some nice function. Fourier transform of a function f from real numbers to complex numbers will be defined as follows. F of xi is equal to the integral over the whole of r, f of x multiplied by e to the minus 2 pi I x xi dx. Okay? So this is kind of a general construction. It generalizes to locally compact abelian groups. So if you take R to be your group of interest, then you take any nice function, multiply it by all possible additive characters. So what?
X в степени кси или просто x кси?
X умножить на xi. X multiplied by xi. So functions of the form x goes to e to the e to the 2 pi I psi x are additive characters of this group, right? If you add x's together, then you multiply the values of characters. And here you kind of get a scalar product of your function with a given character. Okay, so in some sense, Fourier transform takes values. Domain of Fourier transform is not real numbers, but the dual group of real numbers. But we are lucky, and this is still the same as real numbers. Okay. So this is very highly non-arbitrary. So we will consider this. Also, as we are doing number theory, we do not have 1 over square root of 2 pi outside the integral, and we do have 2 pi inside the exponent. This is because we are doing number theory, and so we want our characters to be, we want integers to pair with themselves trivially. So if you take x and xi to be integers, then your character will be 1. Okay, so what is the lemma? Suppose that f is from real numbers to complex numbers, and sum of f of n. Sorry, I will require something else. So this will converge uniformly in x. So our function is, it goes to 0, say, fast enough. For example, f of x less in order than 1 over absolute value of x squared plus 1 will suffice. So we require this convergence, and we also require that sum of Fourier transforms of f is less than infinity also. Okay? So our function goes to 0 fast, and its Fourier transform at integers also goes to 0 fast. Okay? For example, this of course will. Sorry, maybe it's incorrect. F should also be. Okay, so we will assume that f is nice, like smooth, something else. Okay? Что такое?
Вопрос, у нас суммирование вообще по каким...
Summation is over all integers. Sorry.
И во втором именно икса нет, да?
Нет, во втором икса нет.
Сейчас.
Мы увидим почему.
Можно тогда про первую сумму пояснить? Еще раз. У нас есть...
У нас есть вот эта сумма,
Да,
она зависит от икса.
Да.
Для каждого икса она сходится, причем сходится равномерно. Ну, вы можете там обрезать на месте минус n и n, и она будет сходиться, в общем, с одинаковой скоростью. Как хотите, в общем. У нас well, we will not care about the precise formulation because our function will be nice, it is enough to assume that f is smooth and its Fourier transform is smooth. Then everything will be okay. You can assume that.
F is smooth isn't stronger than this.
What?
Isn't F and F's Fourier transform are smooth stronger than this assumption?
Of course, it is very much stronger. But you can assume even more. You can assume that f is a Schwarz function. Schwarz function is a function which goes to 0 faster than any inverse of polynomial, and its Fourier transform should also go to 0 faster than any polynomial. This function will be smooth, and its Fourier transform will also be smooth. Okay? We will not apply this formula yet for any non-nice functions. Okay? Actually, our function will basically be an exponent. Okay, so what is the statement? Then we have sum over all integers n. F of n is equal to the sum over all integers m, Fourier transform of m. This might be kind of a bit surprising because one expects then if you take that if you take a function, you can change it a little bit at integers, for example, and then you get. Sorry, maybe we should also assume that Fourier transform goes to infinity fast, to 0 fast, but it's all technical details. Okay, so this is a bit surprising because for some reason, if your function is nice, then its Fourier transform knows everything about its values at integers. This is maybe a little bit less surprising because if you already know that, for example, Fourier transform is always invertible, and if you take Fourier transform of Fourier transform, you get to the original function up to some obvious changes. Okay, so how to prove this result? This is, by the way, lemma 1 is called Poisson summation formula. And it also generalizes to a vast extent. Okay, so let us prove this result. So consider f of x sum over all n integers f of n plus x. This is a nice function, correct? So sorry, maybe I actually need something more. Maybe f should be continuous. But okay. So this is a function, and it is f is one periodic, right? So it has Fourier series. What?
If it's one periodic, you just want to have Fourier series, then you don't need.
Yeah, I want Fourier series, and then a posteriori we will find out that Fourier series is absolutely convergent. And if you, maybe you can assume that that this is continuous, and that f is also continuous. Okay.
No, I mean, you don't need the f is continuous.
What?
You don't need it's continuous. You just want. You can just.
Yeah. Fourier series is always there if you know that the integral is convergent. Correct. Yeah. So f has Fourier series, and what is a Fourier series? F of x is equal to sum over all m integers, Fourier coefficient of m multiplied by e to the 2 pi I mx, right? And how to compute the coefficient? Can someone please tell me what is the coefficient of Fourier series?
Something like
Huh?
we have to multiply by e to the power of minus.
Correct. So you take integral from 0 to 1, f of x, multiplied by e to the minus 2 pi I mx dx, right? This is basically a formal identity, and if you know that your f is from L2, then this is an identity of two elements of a Hilbert space, right? But more is known. For example, if your f is continuous and its Fourier series is absolutely convergent, then this is an identity of continuous functions, right? Okay, so let us compute the coefficients. F hat of m is equal to integral from 0 to 1, sum over all m. Sum over all n integers. F of x plus n e to the minus 2 pi I mx dx, right? By definition. So now I will carelessly change integration and summation because I spent like 10 minutes describing how nice our function is. Okay? So this is sum over all n from integers, integral from 0 to 1, f of x plus n e to the minus 2 pi I mx dx. Now, in this integral, you can shift a variable from 0 to 1 to from n to n plus 1, right? So x plus n will be your new variable. This is equal to the integral from n to n plus 1, f of, say, capital X, e to the minus 2 pi I, m capital X, d capital X. Correct? Or did I miss something?
X в степени ешки нужно заменить на x минус n.
У нас
Нет, там же будет
еще
3
секунду.
минус 2.
Correct. I missed x minus n, but e to the minus 2 pi I mn is equal to 1. So this identity is actually true.
Сейчас. Еще раз, у нас этому интегралу что равно?
Слагаемое. n слагаемое равно вот этому интегралу. В каждом слагаемом
Да,
поменяем
понятно.
переменные.
Да, понятно.
А вот это все как раз за счет того, что мы полагаем, что наша функция какая-то супер хорошая.
В смысле, что можно поменять
Да.
интегралы местами. Ну, для этого достаточно сходимости,
Ну,
например.
да.
Can I ask you what's the worst condition for f to make you change this?
What is the worst condition? The worst condition I am aware of is something like absolute value of f of x is at most x plus 1 to 1 plus epsilon, and absolute value of f hat of xi is something like this. You can actually replace this function on the right by any function with absolutely convergent integral. So basically, if you assume bounded. No, I don't actually know. Sorry, this is a lie. This will suffice. This will suffice for sure. But it is non-trivial to prove that this will suffice, as far as I remember. No, maybe this is obvious. I don't remember. I remember that if you require f and f hat to be in L1, then this will not suffice. There are counterexamples. But if you are interested with optimal form of Poisson summation formula, then read Zygmunt and Calderon, please. It contains a lot of this stuff. Okay, so what to do now? Now we have integral from n to n plus 1 for any n. Of course, the sum of these integrals glues into the integral over r f of x e to the minus 2 pi I mx dx, right?
Тогда вопрос, не стоит ли нам тогда вот в этом вот, короче, когда мы заменяли слагаемое, может нам стоит заменить все-таки x в показателе экспоненты на x минус n?
Correct. Once again, you can replace this x by x minus n, but then you get an additional factor of e to the 2 pi I mn, which is equal to 1. This is why it is crucial for us to use this normalization of Fourier transform. Otherwise, this will not work, right? Okay, so this is precisely the value of Fourier transform of of f at the point m, right? So Fourier coefficients of your function are actually Fourier transforms of the initial function f. Now we know that these coefficients are in L1. This means that this identity holds not only for functions in L2, for elements of Hilbert space. This is true pointwise. True pointwise due to absolute convergence. Also about continuity, of course, you should assume that your little f is continuous. Otherwise, it is, the formula. What?
Pointwise это по-русски.
Поточно. Верно, в каждой точке. Не просто как функция. Ага. So,
Кстати, откуда это непосредственно следует?
Что следует?
Что верно в каждой точке.
So this statement is about Fourier transforms of continuous functions. It is known that if you have a continuous function on an interval from 0 to 1, and its Fourier series is absolutely convergent, then it is equal to its Fourier series pointwise. It is a known result from Fourier analysis. Okay, you can prove it using something like Dirichlet kernels or something like this. Okay, so f of 0 is equal to sum over all m from z f hat of m, and f0 by definition is equal to sum over all integers f of n, which concludes the proof, right? Nice. What can we do next? Next, we are going to specialize our formula to produce some non-trivial identity. And from this non-trivial identity, we will deduce the functional equation. Lemma 2. Take.
Извиняюсь, мы еще раз, как f от x определяли f большой от x?
f большой от x это вот эта сумма.
Нет, стоп, это же у нас...
Это f большой... Нет,
с крышкой.
нет, это сумма под интегралом, я же говорю.
Да, все понятно, спасибо.
Окей? Работало?
Ну, вроде да.
Nice. So, take a parameter t greater than 0. If f sub t of x is equal to e to the minus p t x squared, then the Fourier transform of f at the point xi is equal to what? Maybe someone knows. Okay, so maybe I'll stop it. 1 over square root of t f 1 over t of xi. Okay? So it turns out that if you take this family of functions, exponents of something quadratic, then the Fourier transforms of these functions are related to the same family.
Can you reduce this by like integrating some function on complex plan?
Of course,
How?
we will do it. Okay, so to prove...
But I thought you want to prove it, reduce this from lemma 1, correct?
No, we will prove this separately, and then this together with lemma 1 will produce some non-trivial identity. Okay? Does this sound like a plan?
So I mean, from lemma 1 you should have this.
No.
So if you don't take x equals 0, then I think you should.
I don't know how do you deduce this from lemma 1?
From Poisson summation.
No, Poisson summation requires knowledge of some Fourier transform. If you do not know the Fourier transform of a function, how can you deduce the Fourier transform of a function? I don't know. I don't know what you're talking about. I'm sorry.
I also don't know why you're talking about.
So let me prove this formula. Proof of lemma 2. So f sub t hat of xi is equal to the integral over real numbers e to the minus pi t x squared minus 2 pi I xi xi x dx, right? When you see such an expression, what is the first instinct for you?
Fear.
What? No, I mean like this, not like an integral of exponent. No, you see this stuff inside the exponent.
Полный квадрат.
Sure, you can complete it to a square. So note that minus ptx squared minus 2 pi t x squared, sorry, minus 2 pi I xi x is equal to minus pi t. Then you have x minus plus I xi divided by t squared, right? And then you should subtract the square of this stuff. So the square of this stuff is minus xi squared over t squared, right? So it is plus xi squared over t squared. Correct? Now, integral over r e to the minus pi t x squared minus 2 pi I psi x dx is equal to integral over r e to the minus pi t x plus I t xi over t squared. And what did I miss? I missed minus pi psi squared over t dx, right? Then I would like to say that the integral over x is the same as let me write this. This is the integral over r e to the minus pi t x squared minus pi psi squared over t dx. So this is not exactly true, because to prove this you need to shift your variable by something complex, right? But let me do a little trick. Well, this function is obviously holomorphic in xi, right? Correct? So this is holomorphic in xi, so you can assume that your xi is completely imaginary, right? Then this identity holds because you shift your line, right?
Yeah, but you can also do counter integration.
Yeah, you can do counter integration, but I don't want to. I just want to use identity principle.
How do you use identity principle? I know how to use counter integration.
Once again, notice that this and this are both holomorphic functions, right? They are globally holomorphic due to convergence of integrals. Now assume that your psi is actually imaginary. If psi is imaginary, then this number is real. So you can actually shift your integral by something real, and then you get an identity, right? So if xi is imaginary, then the functions are equal. And if two holomorphic functions coincide on the imaginary line, then they are equal to each other, because, their difference will be 0 on the whole line, and this cannot be. Okay, so this is easily checked to be equal to 1 over square root of t multiplied by e to the minus pi psi squared over t, right? This is, the exponent comes from the exponent, and 1 over square root of t is due to the formula integral over r e to the minus pi x squared dx is equal to 1. To prove this formula, you need to take your integral, square it, and then use polar coordinates, for example, right?
Yeah, because when you use that, it gives you pi.
Yeah, of course. Okay, so this is an exercise if you don't already know this formula. Что?
Интегрировать чертать надо на курсе. Когда там считать.
Интегрировать что надо?
Конечно.
Of course you should integrate, because it's a course in analytic number theory. And when you go to algebraic number theory, you don't only deal with numbers, you also deal with matrices, modules, and so on, right?
Sheaves.
Что? And sometimes even also with integrals when you do algebraic number theory. Okay, so we proved our lemma 2. Let us deduce a corollary of lemma 1 and lemma 2. If theta of t is equal to sum over all integers e to the minus pi n squared t, then theta of 1 over t is equal to square root of t theta of t. Okay? So this formula follows immediately from lemma 1 and lemma 2, right? You just take theta of t is equal to sum of f sub t of n over all integers. And this is by lemma 1 equal to the sum over all m, f sub t hat of m, which is by lemma 2 equals sum over all m, 1 over square root of t, f 1 over t of m, right? And this is equal to 1 over square root of t, theta of 1 over t.
Is this related to the theta function?
Oh, of course. You can observe that if you set t to be minus I tau, then you get the theta constant, right? This is precisely the modularity of theta constant checked on the imaginary line. Окей.
Что такое модулярity?
Это другой вопрос, и это не в рамках этого курса, пожалуйста.
А в какого?
Приходите на автоморфные формы и приложения. Ну, вообще потом у меня спросите просто. Ага. So now from this corollary we will deduce functional equation, but first let us look at this identity a little bit more and deduce something funny. So take this formula. Let's take a derivative. What we are going to get? Theta prime of 1 over t multiplied by minus 1 over t squared is equal to 1 over 2 square root of t, theta of t, plus square root of t, theta prime of t. Right? Now let's substitute t equals 1. Then minus theta prime of 1 will be exactly equal to theta of 1 over 2 plus theta prime of 1. Correct? Открыть?
Да.
Закрыть.
Открыть.
Ага. Даешь свежий воздух. Okay, so we have this identity. So minus 4 times theta prime of 1 is equal to theta of 1. Correct? Now let us use some approximations for theta. Of course, theta of 1 is equal to 1 plus 2 times e to the minus pi, and then you get 2 times e to the minus 4 pi, and so on, right? So e to the minus 4 pi is something very small. E to the pi is around 20, so e to the 4 pi is around, well, what? It's around 16, like 160,000, right? So theta of 1 is approximately equal to this, right? And theta prime of 1 is approximately equal to, well, if you take a derivative, then your constant term will vanish, and then you get minus pi multiplied by this. So this is minus 2 pi e to the minus pi. Correct? So from this you get that 8 pi e to the minus pi is approximately equal to 1 plus 2 e to the minus pi. Right? So e to the pi plus 2 is approximately 8 pi. Let us compare these values a little bit. So 8 pi is approximately equal to 2,5,1,3,2,7,4,1,2. Okay, and e to the pi plus 2 is approximately equal to 25.140696. So the difference is in the second digit. And this is, it turns out that this is not just a funny coincidence, this is also one of the phases of this functional equation.
А случайно с такой точностью не получается? То есть если мы все формулы подобной сложности выпишем, то там не будут случайные примерно такой же точности?
Можете попробовать. Я не знаю. Okay. Now what? Now we are going to deduce the second theorem, the functional equation for Riemann zeta function. First of all, notice that pi to minus half of s, gamma half of s, n to the minus s is equal to integral from 0 to plus infinity x to half of s minus 1 e to the minus e to the minus n squared e to the minus pi n squared x dx. Okay? This formula is true due to, say, linear change of variables. If you set y to be pi n squared x, then you get pi to the minus half of s from x to the half of s minus 1, and then you get n to the minus s from the same thing, and then you are left with the integral for gamma function. Okay? Now, I will ignore all the issues with absolute convergence because I can. But this is an exercise for all the interested listeners to fill the gaps with possible gaps with analysis. Okay, so pi to minus half of s gamma half of s zeta of s is equal to integral from 0 to plus infinity x to half of s minus 1. And now what we get? Sum over all n from 1 to plus infinity e to the minus pi n squared x dx. Right? Well, if you ignore the issues with summability. Okay? Now, this one is, of course, closely related to theta. Let us name it as something. What? Alpha. So this will be alpha of x. Okay? Now, by corollary, alpha of x is equal to theta of x minus 1 over 2, and alpha of 1 over x is equal to theta of 1 over x minus 1 over 2, right? So it is equal to square root of x, theta of x minus 1 over 2, which is equal to what? Which is equal to square root of x double alpha of x plus 1 minus 1 over 2, right? This is by definition, and this is by corollary.
Сейчас разумеешь. А у нас же в предложении было, что мы за тета от t обозначаем вот ровно то, что мы обозначили за альфа от x.
Нет, неправда. Там сумма по всем сторонам,
Все, понял.
Okay, so this thing is equal to alpha of x plus square root of x minus 1 over 2. Correct?
Корень из x на альфа x.
Yeah, sure. Thank you. Square root of x, alpha x, plus square root of x minus 1 over 2. Right? Now, what can we do next? Next, we are going to notice something. So, our integral can be a little bit divergent, right? If your s is small, then alpha is close to sorry, нет, неправильно. I am incorrect. So if s is small, then x to the s over 2 minus 1 has a singularity at 0, and alpha, alpha is also unbounded at 0, so sometimes you get a divergence, right? So it is not immediately obvious that zeta is holomorphic. But we can deal with this issue as follows. Integral from 0 to plus infinity, x to the half of s minus 1, alpha of x dx is equal to integral from 1 to plus infinity plus integral from 0 to 1. All the same thing, right? Then I'm going to transform the second integral to the integral from 1 to plus infinity, using x to 1 over x. So the first integral will remain unchanged, integral from 1 to plus infinity, x to half of s minus 1 alpha of x dx, and then we are going to get integral from 1 to plus infinity, and then what? Then 1 over x to the power half of s minus 1, alpha of 1 over x, and dx over x squared, right? Next, this is equal to square root of alpha of x plus square root of x minus 1 over 2. So now we are left with the following. Integral from 1 to plus infinity, then we get x to half of s minus 1. Let's group it with the second term here. So you get x, this one is x to 1 minus half of x, half of s, x to the power 1 minus half of s, then divided by x squared, you get minus 1 minus half of s, and you get additional half from square root of x. So you get x to the power 1 minus s over 2 minus 1 multiplied by alpha of x dx, right? And then you get some easy integral. Let me write it down. Integral from 1 to plus infinity, x to 1 minus half of s, square root of x minus 1 over 2 dx. Okay? Now, this last integral can be explicitly computed, right? This is, say, r of s. Let us compute r of s for the sake of completeness. So r of s is equal to what? It is equal to half of the following difference. Integral from 1 to plus infinity, x to 3/2 minus half of s dx. Oops, maybe I missed something. Sure, minus 1. This is because I forgot to divide by x squared, right? So it is not 3/2, it is 1/2 still. So it is 1/2 plus, minus, sorry, integral from 1 to plus infinity, x to the power minus 1 minus half of s dx. Right? And integral from 1 to plus infinity x to the v dx is equal to what? It is equal to 1 over minus 1 over v plus 1. Right? If what?
If v is negative.
If v plus 1 is negative. For real part of v plus 1 less than 0. Correct? So we can assume this holds for these two integrals, right?
Ну, у нас там плюс 1/2 и минус 1/2. У нас было x в степени минус 1 минус s пополам. Мы умножаем это на x в степени 1/2. Нет, так мы же пишем...
Значит,
нет, потом...
x в степени 1
Нет,
минус
здесь
s пополам.
все понятно. Вот мы
Вот здесь,
рассматриваем
верно?
rs. Да, здесь минус 1 в степени минус s пополам.
Здесь тоже минус.
Там тоже минус должен.
Ага. Thank you. Yeah, we also missed some minus here. Thank you very much for the help. Okay, so this holds, right? We can assume that real part of s plus 1 over 2 is positive, right? For example, we can assume that real part of s is positive. Then this will all converge and equal to 1/2 of the following, of the what? Of the minus 1 over 1 plus minus 1/2 minus half of s and minus 1 over minus half of s, right? This is a simple computation. So this is equal to what? To what? It is equal to 1 over 1 over s minus 1, right? Plus no, this should be
Minus 1 over s.
yeah, minus 1 over s, which is equal to 1 over s times 1 minus s. Correct? Nice. What now? Now you see that this function is meromorphic, and r of s is equal to r of 1 minus s, right? Obviously. Now, let's look at this integral. Where are the possible problems of this integral? Well, we eliminated the problem at 0, so the only problem with this integral is that it is improper, right? So the only problem is at infinity. But your alpha goes to 0 exponentially at infinity. So for any s, this integral is absolutely convergent, right? It is obvious that alpha goes to 0 exponentially, because from the definition of alpha, it starts like e to the minus pi x plus e to the minus 4 pi x plus and so on, right? So this integral is actually holomorphic. This is because it is an absolutely convergent integral of holomorphic functions. Okay. So our function here, so pi to the minus half of s, gamma half of s, zeta of s is holomorphic outside of s equals 0 or 1. At 0 and 1 it has simple poles, and it is symmetrical with respect to s goes to 1 minus s. So it is invariant to this change, right? Because R of s is invariant, and this stuff is also invariant tautologically. Correct? So we actually have a functional equation for the Riemann-Zeta function.
Yeah, but
Yeah.
So you have this functional equation, and at every point you should have a proportion, a fixed point. You know the gamma function. You should have a proportion of zeta s and zeta 1 minus s. But how can you say you know about you are sure about the value of zeta s?
So once again, we have this function psi of s. It is called Riemann's psi function. We know that psi of s is meromorphic, and it satisfies this functional equation, right? And we knew automatically that it is meromorphic in this half plane, real part of s greater than 0, right? And with respect to this symmetry, your half plane goes to the half plane real part of s less than 1. As these two half planes overlap in the intersection, so between this line and this line, you know that your function is symmetrical, and it is also defined inside this strip, right? So by identity principle, these two functions are actually equal to each other, and so you get a continuation automatically, right? So I am out of time, but I can still say something very quick about zeta function. So this picture is actually very relevant. So you have 1 here and 0 here, and well, zeta function converged automatically in this region. Then we continued this function basically obviously by partial summation in this region, and then we continued it here by the functional equation, right? So this strip will actually be the most interesting set to understand the Riemann zeta function behavior on, because here we have convergent series, and here we also have convergent series up to some some gamma factor. And here we have something mysterious, right? So this strip is called the critical strip. And inside of it, we have a line real part of S is equal to 1/2. Can you guess what is the name of this line?
The critical line.
The critical line. And it is known that all the interesting zeros of zeta function lie inside the critical strip. What is an interesting zero, we will understand during the seminar. And it is conjectured that all the interesting zeros, on the non-trivial zeros, lie on the critical line. This statement is called the Riemann hypothesis. Next time, we will continue to study the properties of Riemann zeta function as a function of complex variable, and we will also relate the distribution of zeros of zeta to the distribution of prime numbers. Of course, from today's considerations, it is completely non-obvious what the relation is, right? Okay, that's it for today.
Where do we have the seminar? Where do we have the seminar? In
На каком здесь? Я не знаю. Здесь, да?
Вроде как, да.
Говорил, что может ставить на паузу и вспомнил. Так что он поставил, что у нас будет.
Сейчас, а он разве не 2 слода сделал в этот раз?
Вот, я говорю.
Все, по идее пошло.
Okay, let us start. Today we have 6 problems, and at the end there are some formulas. Formulas with gamma function. We will not prove them. They are standard formulas. For example, you can read about them in this book. We will just use them. Okay, and there is a formula at the end of the paper that you on the lecture you've proved that if C of S is 1/2S S minus 1 S over 2 gamma S over 2 zeta of S, we prove that C of S is equal to Xi of 1 minus S.
Xi по-английски Xi.
Xi, okay. Xi. And there is equivalent formula, and I want you to prove that this is equivalent. It's equivalent when zeta of S is equal to 2 to the power S, P power S minus
Pi.
pi sine of pi S over 2 gamma of 1 minus S zeta 1 minus S. Okay, claim that this is equivalent, and today on the seminar I want to look at the different proof of functional equation, and we will prove the second formula. Okay, so here you can use these formulas about gamma function. Actually, you will need such an identity. It's reflection formula. Gamma of S multiplied by gamma 1 minus S is equal to pi divided by sine by S. And
We will prove it.
no, I thought that you can see the proof. Actually, it is equivalent to the product formula for sine.
Of course.
And second formula, it's Dublin formula, I think. Gamma 2a, gamma 1/2 is 2a minus 2a minus 1, gamma of a plus 1/2. Okay. Yes. Of course, if you know such a density, for example, for real S, by holomorphic continuation, you know it's for every complex S. Okay, anyone can.
And Dublin formula we can actually do.
Dublin formula, oh yes, it's more trivial.
Anyone?
Show that with equation. Please. Yeah, I can. So you need to write this identity, then divide by the left hand side, and then use these two identities.
Divide what by what?
You want to write that z to s. Okay, I can start to write it.
So wait, I'll tell them. So let's take this functional equation and then rewrite it so that you have z of s on the left hand side and some strange product on the right hand side. Okay.
What of this you need to prove?
We need to prove
the
that
equivalence.
they are equivalent, these formulas, these two formulas.
We need someone brave.
Please, yes.
I'm brave, but I have no idea.
It's okay.
Just start to write on the desk, on the board,
I need a
and
couple of seconds.
okay.
Yes, don't.
So first of all, you see this two multiples way this if we change s to 1 minus s, this remains the same. So we have such identity.
Вообще задача у нас сейчас происходит.
Что?
Какая у нас вообще задача сейчас происходит?
Пока никакая.
Yes. We just want to prove that on the bottom you have two formulas. These are two functional equations. It's the same equation. This and this. Yes, this by definition.
Давайте же помним, пожалуйста.
Yes, now you write z of s is equal to, and divide by this, yes? You'll get zeta 1 minus s, and here pi to which power? S minus 1/2, yes?
Right?
Gamma 1 minus s 2 divided by gamma s over 2. Okay, now we want to understand something about this term. Okay. And
Ой, а мы запустили трансляцию?
Да.
Спустя отлично.
Вторая имеет анализ.
Let's apply this reflection formula. I wanted to say that 1 over gamma of s over 2 is what from this formula? It is sine p s over 2 divided by pi, and what? Gamma of 1 minus s over 2, yes? it's just this formula. And now you see this this argument and this argument, they are different by 1/2, and we can apply the second formula. Okay.
Yeah, so from this nice formula we get this strange non-symmetric formula.
Yes, strange non-symmetric, but sometimes more clear formula. Okay, maybe you can believe at this point.
So take A as equal to what? As
A,
as
1 minus s over 2.
yes, A is 1 minus s over 2. You see, we have sign already here. 2 to the power s. This formula will give us. Okay.
Wait, what? We are going to get.
I thought minus s over 2 should take A as minus s.
Yeah, correct. We should take minus s over 2 because otherwise we are going to get some cosines, right? Something strange is happening.
No.
Yeah,
This is
sure.
A. Last one.
No.
No.
If you take A to be 1 minus s over 2, then you are going to get. Okay, we already have signed by.
Yes, we already have signed. Oh, okay, let us continue. I think I just say that this is our functional equation. And this function I will denote, maybe it will be useful later. Here we have
Chi.
chi. Yes.
Chi.
Okay.
In English, you write it as CHI. So it's read as chi.
How to?
What's this in Greek?
So?
Okay, I think number one, you can
Я думаю.
gamma of s and to the power minus s. We want to prove that it is equal to integral from 0 to infinity x to the power s minus 1 exponent of 1 minus n x dx.
So how to prove this formula?
Let me remind you that gamma of s for if let us write s is sigma
S is always sigma plus IT.
plus
by the way.
nt, yes, with real part, and
sigma
for sigma greater than 0, gamma of s is integral from 1 to infinity x to the power s minus 1 exponent of minus x dx.
So how do we prove this formula for gamma of s n to the minus s? Anyone?
Some integration by parts.
So what needs to change so that we arrive from this integral to that integral?
Minus nx is to turn to minus x.
Uh-huh.
So we may change the variable, but then
Mm-hmm.
Can you write please?
okay. So we have to take some other variable to take it as nx. Then like this, and then we have this integral infinity x minus 1 e to the power x dx turns into integral
again from 0 to infinity. What is this? Y divided by m. S minus 1 into the power of minus y. And then here we have 1 over n dy. Now, so probably
Yes,
now we can take n to the power of minus s out. Then we have here no, we have s minus 1 here, so it's a bit but we have this 1 over n, so it doesn't matter. So we have still y s minus 1 into the power of minus 1. And this is just this.
Okay, okay. And I think you can do part B? No, because it's follows immediately. It says that zeta of s is equal to write it, gamma of s multiplied by zeta of s is equal to such integral x to the power s minus 1 over x minus 1. Of course, for sigma
So
greater than
this has to be corollary of A.
greater than 1.
So where do we have n to the power of minus s here?
And we sum over.
So we should sum this over n.
Uh-huh.
Well, let's try. Sum n natural, let's see. Gamma of s minus s, is that right? This is just gamma of s zeta of s, am I right?
Yes.
Then, and also this is equal to, what is this equal to? This has to be equal to this. So we should consider gamma as integral here, I guess.
We should sum this over n.
And we can interchange sum and integral because
Yes, because everything is very well converged.
I don't know why, but we always do, so we can do it probably. Yeah, and this is just a geometric.
What do you mean you don't know why? This is Fubini theorem, right?
Well, yes, but no one remembers the exact. I always remember Fubini theorem as yes, you can interchange always. So I don't remember the exact how exactly it is formulated.
You can if the double integral is absolutely convergent, right?
Yes. Okay. There are many formulations.
Or you can just take a finite sum and then take the limit of both parts.
Yeah, and then by dominated convergence or something like this.
Yeah, and then this is just a geometric progression, I guess. So we just get, if we interchange,
Yes, yes.
we just get, we'll get exactly this.
No.
No?
First you need to write down the
Ah.
geometric progression, and then you'll understand.
Well, it's. So it's like.
So it's x to the s minus 1, right?
Yes, so like e minus 1.
Minus x. Minus x.
Minus x, yeah. Plus e minus 2x. So each time it is just multiplied by e to the power of minus x. And so.
dx.
Don't forget dx.
Dx, yes.
Yeah. Yes.
And then it's just. There's minus x, right?
Mm-hmm.
Oops.
Please just compute this to know. So what's this progression? It will be.
So 1 minus e to the minus x, am I right?
Multiplied by
The first term.
first term, yes.
The first term, e minus x, right? Yeah, that's
And
right.
now we can.
E minus x, and then we take the product of both the denominator and by e to the power of x,
Yes,
and
yes,
we
and
get.
the dessert.
Yeah.
That's it.
That's it. Okay, some little remarks. On lecture, you proved very similar identity, but here it was n square and
Pi and square.
yes, pi n square, and
And
here
half s.
yes, and here you got yes half s.
Of course, I did not prove it. I just spoke over it.
Yes, but it's the same calculation. And another remark is that here we proved our identity for real part of s greater than 1, because we want that our sum 1 over n to the power minus s, that it converges to zeta of s. But now you see that this integral is convergent for when real part of s is greater than 0. So we get yes. What's wrong? You mean e? Okay.
No, it isn't.
Okay. Yes, I forgot that in the denominator.
X minus 1 has 0.
Yes, has
when
0.
X is equal to 0.
Okay, so it's-
around 0, this behaves like x to the power s minus 2. So it is still
Yes, okay.
convergent
So
only when
yes,
sigma is
okay.
greater than
It's
1.
not even analytic continuation. Okay. Okay, but on the next problem we will get analytic continuation. Let us consider such contour. I will denote it C. It starts from real axis. You put it
From real infinity?
Yes, from real infinity goes this way, around 0 and no direction. And let us integrate this function.
Over the curve.
Yes, over contour. Let us denote I of x is such integral z to the power s minus 1.
Сейчас у нас контур получается просто вокруг нуля.
Нет, в смысле просто вот нарисован.
Ну, нет, я имею в виду, что он именно когда сворачивает, просто не очень понятно, как он, ну, короче, на английском описать не очень понятно.
Вот
Here,
нарисован.
То есть просто вокруг нуля он по эпсилону окружности.
yes, and it's important that
Singularities.
singularities of our series they are out.
Вот series function.
Yes, because here we have singularities in these points, and okay, and we want to express this integral in terms of previous one.
Interesting question for the participants of the seminar. Why do we avoid the real axis here?
Because we want to approximate.
Because we have such function z to the power s minus.
S minus 1, and if s is
If z is near, yes.
if s is non-integral, then z to s minus 1 is not a meromorphic function, right?
Ветвление как бы.
Ramification.
Yes, we have ramification at 0.
Наверное, кстати, я не знаю. То ветвление, которое в алгебре, оно ramification.
Окей.
А которое в анализе? Branching, правильно. Это другое ветвление, это branching. Okay, so z to the s minus 1 is not a function on complex plane. Z to the s minus 1 is actually a function on the Riemann surface of logarithm. And if you cut if you cool. If you cut the plane along the real axis, you can consider this locally as two different parts. How to say it? Кстати, вот да, интересно. Два листа как бы накрытие. Тут sheets.
Ну, branches, наверное, тоже.
Не совсем.
Okay, let's just compute this integral now.
We want to evaluate this integral in terms
of
the
our original. First of all, in terms of our original integral, let's assume that sigma is greater than 1.
So that everything converges.
Yes.
So any ideas?
Okay, we can compute, first of all, we can compute our integral over such line. What it will be? Yes, it will be just minus this integral. Okay, and now in the origin of 0, what it will be? I claim that if...
We have no residues yet because we don't have any...
Yes, there is no residue at 0 because it is not a function on the plane. Yeah, but I claim that if we can assume that sigma is large, then this integral tends to 0.
So we take small. You can replace your circle with a small circle due to Cauchy formula, and then you can send the radius to 0, and assume that sigma is large. You will get 0, right?
Sigma is greater than 2.
А сверху какая-то штука.
Если большой сигма там больше, чем
3. Когда все получится, например.
больше, чем 3.
Ну точно. Okay, so this will tend to 0. We prove our formula for large sigma. And now, what's the integral over this line?
Minus this.
But there will be some.
No, here was minus, yes.
Let's denote this integral by j, please. I'm tired of hearing this is equal to that.
Because this function has, it is 1 over z, yes? And this function, if sigma is large, it is...
It has 0 of large order, basically.
Yes.
Large fractional order.
Now, you see...
So I of s is equal to I1 plus I2, right?
we write that I of s is minus j of s plus what? This from integral over this line. Now, what is z to the power s minus 1 by definition?
G от S это кто?
Это вот тот
This is
Ah.
such integral. Z to the power s minus 1 it is exponent of logarithm z
by s minus 1.
yes,
Of course.
multiplied by s minus 1. And now, what's logarithm z? It's the branch of logarithm. Actually, it is logarithm of absolute value plus I argument of z. And this argument, it is not, there are several possibilities for it, but we want it to change continuously. And
Yeah, it's gonna enlarge by 2 pi.
yes, here it is 0, and when we round, and it becomes 2 pi, yes. So here we will get exponent of logarithm z s minus 1. It's the same function as it was, multiplied by 2 pi I s minus 1. Yes?
Yeah, so this is an example of monodromy, right? We circled around the zero and we experience the monodromy of our logarithm.
Yes. And so plus what? Plus e 2 pi I s minus 1. Actually, we can write s because 2 pi I, e exponent of 2 pi I is 1. So this is s, g of s, j of s. And now we know that I of s is what? It is j of s.
Divided by?
Yes.
Multiplied by, sorry.
Plus.
Multiplied by e to the
Yes,
2 pi
yes, yes.
s minus 1.
And from the previous formula, we get the first identity. Okay. Zeta, what we want to prove, zeta of s is, let me write it separately. That's what we proved. 1 over 2 pi I s minus 1 gamma s integral. Okay.
By the way, at the first glance, you can think that this formula cannot be true, because if you substitute s to be a positive integer, then you get a pole at the denominator, right? But if s is a positive integer, then due to Cauchy formula,
Yes,
you get
yes,
0
yes.
from the integral. And they cancel out and you get zeta function.
Yes, and somehow a second, it's reformulation.
Еще раз. Кажется, что эта формула это безумие.
Yes, we know that for you mean.
Сейчас можно я скажу, да? Значит, кажется, что эта формула это безумие, потому что если вы возьмете туда поставите s равно 10, то у вас экспонента минус 1 станет равна нулю, и написано, что z от 10 это бесконечность. Да, но на самом деле следует обратить внимание, что когда s равно 10, то интеграл равен нулю по формуле Cauchy.
Okay, and do you understand the last identity?
Where does the last identity come from?
Як формулу для гамма функції Хромова описывали?
Yes, from reflection.
Гамма S cancel plus minus.
Uh-huh.
And where is the sign?
The sign turns into it turns into e to the power of
PIS, PIIS minus e to the power of minus PIIS. Yes, because
2 pi I?
2i.
no PIIS. We multiplied.
It is sign.
Pi s.
I,
Pi s.
yes. Okay.
Ужас, чего ты придумаешь.
Это не мы, это Рима.
Okay, and now this formula is better than the previous one because here this integral converges for every x.
Yes, this integral is convergent because it does not have any problem, right?
Yes, because
It
this
is
function.
zero at infinity, it converges because exponent wins.
Yes, so we get analytic continuation of zeta function for to the whole complex plane.
Yeah, of course, this analytic continuation for the function seems unuseful, right?
But it's actually it's useful.
How can we compute anything like this for any value of s? What can we do next, right?
Ой, там вот на предыдущей доске был какой-то рисуночек с кривыми.
Ага.
Справа. А что это было?
Ну, типа такая
вот
спираль
видишь,
рисует,
это
которая вокруг
Z равно есть
нашей
прямому.
интуиции. Ну, разрезать поэтому и так. Логарифм как обозначить.
Кирилл, конечно,
Yes, next we will use this formula to compute some values of the function and at the end to deduce function equation. Okay, first of all, we have such our series 0 exponent minus 1 is 1, 1 minus 1 plus z plus b2 plus b4 etc. First of all, these are Bernoulli numbers. Do you know Bernoulli? No. Okay. So of course you can compute such series, and there will be some numbers. Actually, B2 will be 1 over 6. Yes. Sir. This is one.
Let me check.
Okay, but it doesn't matter. And
This, of course, is a finite computation.
yes, it's finite computation, and it turns out that odd coefficients they are 0, except for the this coefficient. How we can prove it? Who knows?
You mean from the definition of Bernoulli numbers? Or?
From the this is the definition of Bernoulli
We
numbers.
define Bernoulli numbers like this.
Yes.
Но если эту штуку влево перенести, должна четная функция.
Yes.
So this is my favorite example of a function which is even, but it is not trivial to see that.
Maybe you can check that it is even because you say that you don't understand.
We are proving that zeta of 0
Don't
is...
trivial example of even function.
We want to prove that this is even, четная функция, то есть если на минус z, поменять, то будет то же самое.
Так, мы вот поменяем это на
О, ой, ничего страшного.
Ну, тогда это обозначу.
Можно внизу написать.
Ну, я вот обозначу.
А?
We can use what is written above, right?
No.
No.
We don't know a priori that all the odd coefficients are equal, right? We want to prove it.
Надо будет это что-нибудь.
Так, можно сказать, что это будет равно цвет под цвет.
But what is written above is given to us as a definition, no? So
Yeah, but for this definition to make sense, we should know that there are no odd coefficients beyond.
so we are just verifying that this is a good definition.
Yeah, we are verifying that we are not insane.
I skipped B3 because you can check that it is 0 by computation.
Мы не можем просто если мы сюда вот перейдем, здесь у нас...
Мы пока не знаем
I
этого.
write it. Okay, I can write here B3, and you want to prove that it is 0.
Так. Что нужно сделать?
Вычислено.
that we are given that, but we can't use it. We are verifying what we are given.
Yeah, it's frustrating, right?
Yes.
Получается, плюс z.
Неужели к общему знаменателю будет приводить?
Наверное, просто z. Плюс. Здесь можно знаменатель. Здесь у нас что будет? Тут у нас будет минус 2z. Плюс. Я чуть не замечаю.
Ну, наверное, надо и это к общему знаменателю.
Ну,
Да, нет, хотим.
Почему нет?
Ну,
Должно сработать.
Ну, минус z мы хотим получить, да? Ну, просто, наверное, скобки надо раскрыть.
You just take that out of the brackets.
Если трансакция будет к общему знаменателю.
Да там просто последний можно домножить был на e в степени z. Ну, в смысле...
Тривиальное равенство можно доказать.
Короче, z делить на e в степени минус z минус 1 можно было просто домножить на e в степени z и числитель и знаменатель. Тогда у нас бы все хорошо сложилось и без всяких приколов.
Сейчас так все сложится, не переживайте.
Ну, а тогда все получится.
Рассложим.
Это же, например, чего?
Четной функции. Нетривиальной.
Это, в смысле, неопределенный, как четная буквальная формула.
Ну, в смысле, из которой не видно сходу, что она четная.
Так, ну теперь аккуратненько все скобки надо раскрыть.
В том числе в знаменателе, между прочим.
Да. Так. e в степени z на e в степени минус z. Это будет e в нулевую, это будет единица.
Минус e в минус z.
Z. Минус e в z. Плюс 1. Здесь минус 2z. Здесь плюс.
Ну и все.
e в степени z. Плюс z. e в степени минус z.
Ну и все хорошо.
Да.
Все. Можно не раскрывать знаменатель. 0 получился. Даже?
Да.
Да, вот здесь вот 2z. Ну да.
Ага.
Now maybe you can compute. Do you know Cauchy theorem?
Какую?
Формула.
Cauchy формула.
Which one?
Что интеграл по контуру равен с
Что это
на сумму.
Да.
Okay. So you can solve problem 3. Maybe I can start. You see, we proved such formula for zeta. Let me write it once again. Such integral. And claim that we can find this integral.
We can compute zeta at
minus n, where n is
e to the z, you forgot e to the z minus 1, right?
yes. Maybe we can change here n to s to minus n. Okay. What we will get? Minus n.
Тут будет просто и
Here n.
Без
и
минуса.
плюса. Плюс.
Yes.
Там 1 плюс n.
Плюс n.
Plus plus n.
Здесь
Not
минус n. Минус n.
plus n. And yes, here.
Минус n, минус 1.
And now you can use Cauchy formula because you know coefficients of such series.
Так, формула получается вот для этого. Контур кэш-формула
Контур не важен, понятное дело.
Круг нуля.
Понятно, что эта штука, это 2πe, да? Давайте напишем, что интеграл, да? Интеграл. Z.
Ой, ну да. Ну,
Z. What? No. Don't write the Cauchy formula itself. Let's write it in our case. Z to the n minus to the minus n. What? What? Sorry.
это чисто писать букву.
Не надо.
We
Да,
want to
вычислить
compute
надо.
this integral.
Ну
There is no
это
z
будет просто
here.
2πi.
Here
Which
we get z over we know power series for such function to the power z minus n minus 2d.
Z.
Yes.
And it is equal to the residue, right?
What's the residue?
Write the formula, please. So it is equal to pi I residue, right?
Так, и вот это
2pi I multiplied by residue. Just write
ну,
this.
вот это вот разложение.
Residue res.
Res. Вычет в...
At z,
Я
z
понял,
equal to 0
Вычет в нуле. Вот это вот.
Of all this
of
stuff.
such.
Да, я понял. Так, 1 минус 1/2 z.
P2 z квадрат и так далее, и тому подобное. И еще z в
И
степени.
z в степени минус n минус 2.
So we are interested in the coefficient at z to the minus 1, right? And what is the coefficient at z to the minus 1?
Так, ну, получается, нам нужно отсюда подобрать такой, чтобы суммарно вот с этим оно было минус 1. Это будет, получается, z в степени... Сейчас скажу.
Вынесли уже.
Vn плюс p.
Нет,
Да.
минус
Получается, будет 2π.
где все еще должно в остатке.
Да,
Не в остатке.
под вычетом, естественно.
Первое.
Вычет.
Иначе не
Разделить на n
давай.
плюс 1.
Так.
Ага.
Так, а b плюс первое.
Correct, right?
Yes, correct. And now we can compute this. It's equal to what?
Ну, это, получается, будет e в степени...
Давайте сразу без e.
Yes.
У нас же...
It is 1 or minus 1. Yes?
так, это будет, получается, минус 1 в степени n.
Mm-hmm.
А вот это у нас будет n факториал.
Ага.
Ну, здесь 2πe.
Сократится.
Оно вот здесь сократится, да.
No 2pi I.
Умноженное на b n плюс 1. Деленное на n плюс 1 факториал. Ну и вот это, соответственно, уйдет.
Mm-hmm.
Минус 1 в степени n. bn
Как
плюс
вы считали,
1
вычет?
на n плюс 1.
Берем
Все.
Z минус первый.
In particular, we see that z to 0 is minus 1/2 or minus 1 over 2. And also, now we know that z to minus even numbers, this is 0 because even Bernoulli numbers are 0.
Also this formulas.
Huh?
Odd Bernoulli numbers are equal to 0. So even
Odd,
values
yes.
of this function.
Yeah, but here we have n plus 1.
These formulas, of course, allow you to generate infinite amount of very stupid jokes about infinite number of mathematicians. Знаете, бесконечное число математиков закрыть бар, заказывают одну кружку пива, полкружки пива, четверть кружки пива и так далее.
And actually, you can see these zeros from
From the functional equation.
from functional equations. Yes, but now we are going to prove functional equation. So we want.
These zeros are called trivial zeros.
yes, these are trivial zeros. And
Well, of course, it is a bit disrespectful to call all the negative even numbers trivial, but at least they are controllable, right? And other zeros of zeta are mysterious. The set of all natural numbers as a whole is not really a mysterious set, right?
А вот
Это,
теперь мы знаем,
so, yes,
теперь мы знаем в отрицательных точках и в положительных. Тоже, допустим, знаем из произведения для синуса какого-нибудь.
положительных четных.
Сейчас. Но в любом случае, если мы возьмем положительные четные, и вот там один минус их, то есть отрицательные нечетные, то есть те, для которых числа вернули. Мы получим из формулы симметрии что-нибудь.
Да, вы получите все формулы там, для z от 2k через числа Бернули.
Понял.
Такой наивный вопрос. В чем, собственно, проблема ментальных больших оставшихся людей? Почему именно гипотеза Римана?
Мы увидим.
Мы увидим.
Ну, там сложно.
Ну, понятно, что там что-то сложное, просто интересно, что именно.
Ну, давайте я попробую по-русски концептуально сказать. Смысл в том, что там вот есть критическая полоса. В критической полосе там у нас есть только вот странная формула z. У нас нету хорошего сходящего чарата. Вернее, он есть, но он...
Как мы посчитали для минус 2m?
Вот эта формула, она для всех n верна.
А
мы знаем, что они 0, когда
у нас четные все,
n
да?
плюс 1 ничего.
То есть концептуально как у нас в этой критической полосе нет нормальной формы.
Ну, она есть, но она не полезная.
Ну да.
Сейчас.
Может, потому что у нас есть функциональное уравнение, за ней мы знаем, потому что при часть больше единицы мы все знаем.
Вопрос в том, почему вообще не просто понять про все остальное. Ну вот проблема в том, что сходящегося ряда нет, исходящегося произведения нет, ничего вообще нет.
Нулевое число Бернули, это получается минус 1/2.
Но любое число Бернули это 1.
Да, все.
How to deduce functional equation? We want to compute
Поэтому, кстати,
our integral.
This formula is also true for n equals -1. Because d0 is equal to 1 and you should divide 1 over 0 and then you get infinity.
We want to compute our integral and let us, we have such contour, yes, and let us consider another contour. This is a square, this is point n plus 1.
Multiplied by 2 pi I. You forget to multiply by 2 pi I.
Pi I.
Yeah. Pi I, correct.
So we just go right through the point where it turns to infinity.
No. This turns, this is 0 when z is 2 pi I k. So we go through odd point. So singularities where are...
So we're going to have some singularities inside
Yes.
This is a problem about being brave. So we started by being shy and avoiding all the singularities of our function, and then we are trying to be brave and extend the contour of integration to the whole complex.
Okay, first of all, for example, we can compute our function for sigma less than 0. It will be enough to prove functional equation for such sigma when we extend by analytic continuation. And I want to say that if sigma is less than 0, then such integral tends to 0 when n tends to infinity. Can you see this?
Any ideas?
You can take sigma less than -1 if it's more common.
First of all,
For instance, Маленький, с одно значение.
First of all, this function exponent of z minus 1 to minus 1, it is bounded this contour independently
So
of
when
n.
we go like this,
Because it's periodic. So here it is the same for everyone. And here, here also it is because.
So on this cut part of our previous contour, it is obviously goes to 0, right?
where it obviously goes to zero.
Here.
Yeah.
So now we need to deal with the square.
Yeah.
So what can we do with the square?
Here, exponent of z is small, yes, but we have minus 1, so we have something 1 plus something small. Okay, and what's about this function? Z to the power s minus 1.
Can we estimate z to the s minus 1 on our contour? What is the absolute value of z? Is it large? Is it small? Is it what?
Okay, let me write once again. Exponent.
Oh.
Okay.
What can we say about z to the s minus 1?
Маленький.
Huh?
Где же маленький будет?
Something like this.
Исходить окончательно.
You see, s is fixed, and so there is logarithm is logarithm of absolute value plus I argument, but argument is less than 2 pi, bounded, and imaginary part of s is just fixed. So it's this constant is in big O, and so this is z to the power sigma minus 1, and of course
And
such.
sigma is less than 0. So you have you have a square, and on the boundary of the square, z is of order at least m, right? Correct?
Mhm.
The order of z is m.
By order you mean
The order of absolute value.
okay.
Absolute value of z is like n or something like this. And what is the perimeter of your square?
It is.
Perimeter is big O of n, right?
And so integral of such square is big O of
N to the minus sigma.
Just sigma.
N to the sigma. It's not z, but n.
N, yes. N
Right?
minus sigma. Sigma is negative, we decided. So this tends to 0, and of course, such integral also tends to 0. So now we just need to compute the residues. Who can do this?
The residues in
Of such function.
every point.
In every point inside the...
Yes, inside this contour, so it is 2n pi I minus. So, and actually it is useful to compute the sum of these two residues. You will get sign. Can anyone do this? It's not. Okay, maybe let's do it together. First is it will be minus 2 pi sum of residues because
But we can use the
minus 2 pi I, some residues. And let's compute.
Wait. Minus?
Ну, не разобраешь.
Что?
Типа царем минус, ну, это
sorry, sum of residues, it converges to I of S, right? Sum of residues is some function of n. So it converges to I of S.
We can denote this by IN of S. That's
I n of S. What?
Okay, let's just compute the residue. At 2 pi, 2 pi I, what is it?
Once again, where are the poles of our function?
to by IN.
Yes.
2 pi I m.
Yeah.
And is
Yeah,
already-
okay. Here is that. And now this function is periodic, so just 1 over z, it will be 1 over z.
What?
Ну, вот эта функция она будет.
No, let's just compute the residue.
It will be 2 pi I m to the power s minus 1. Yes?
Correct?
What is?
Residue.
Residue.
2 pi I m is equal to this. This is because the residue of 1 over e to the z minus 1
At
is
0,
equal to 1.
yes, at 0, for example, it's equal to 1, and it's hence at every such point. A plus, let us sum with this residue, it's minus 2 pi I m to the power s minus 1. And now, what's this? It's exponent logarithm of absolute value. It will be 2 pi I m, 2 pi m, I will write, okay, plus argument. And what's the argument of this number?
Yeah, it's just pi divided by 2.
The first one is pi divided by 2.
And let me write. And the second one will be same absolute value,
So, yeah.
but plus what?
3 pi divided by
Yes, 3 because
Because we get minus I.
yes, we go in such a direction. 3 pi over 2 I s minus 1. Okay, and what's this with this absolute value? It will be 2 pi m to the power s minus 1 and also what? E pi over 2 s minus 1 plus e pi 3 pi over 2 s minus 1. And now what's this? 2 pi m s minus 1. And I want to say that here is the
We need to
cosine.
divide by the first exponent, right?
Let me write it in such a way. Exponent of I pi s minus 1 multiplied by what?
Sure.
Exponent of minus I is minus 1
Let's do some trigonometry.
plus is minus 1. Okay? And here you can see that this is cosine. It's minus 2 pi m s minus 1 minus from this exponent I pi s, and this is 2 cosine of s minus 1, and this is sine of what? Sine of
Plus
minus.
plus sine.
Yes, plus sign. Here it is.
And then we sum.
When we sum over m and
and send n to infinity, and we get the functional equation.
yes, because here is m to the power s minus 1, and if we sum over m, we get zeta of 1 minus s, and this formula works for sigma less than 0. This converges. So if you look carefully, you will get functional equation.
Basically, how to prove functional equation for zeta of s? Take the definition, do something, then do anything non-trivial, and you will arrive at the proof of.
Yes, there are many proofs of functional equation, and many different formulas can be a starting point. For example, this formula with integral. And little remark, maybe it's not very useful for our course, but there is a Hurwitz zeta function. It's a little generalization of original Riemann zeta function. It's such sum n plus a. Yes. And I want to say that in the same way, you can prove that it is equal to 1 over gamma s, integral from 0 to infinity, x to the power s minus 1, and here is exponent.
The Hurwitz function can also be used to prove the functional equation.
No, I want to say that it's generalization of zeta function, and it has its own functional equation. Here is the formula you can prove in the same manner as exercise 1, and after that you can do the same stuff. You can take this contour, and so it will be analytic continuation, and you get your functional equation which generalizes our functional equation.
Yeah, by the way, the approach with zeta function can also be used to prove the functional equation for Hurwitz zeta function.
Okay.
I saw the other way around for Hurwitz zeta function to be derived the zeta function.
So suppose you know functional equation for zeta, then we want to derive the functional equation for Hurwitz zeta.
Well, I saw it the other way around.
So it's not
Of course, this will be particular case a equal to 0. Problem number 5. Find all zeros of zeta function in such domain. Sigma is from minus infinity to 0 or from 1 to infinity. So we want to find all zeros out of this crucial.
Yeah, when we solve this problem, we can actually understand why we cannot apply the same reasoning.
Okay, first of all, I think that
That's critical thing.
it's easier to look at the second condition. Why zeta doesn't have any zeros if real part of S is greater than 1. Who knows?
Тут можно подумать хотя бы немного.
А?
We are proving that zeta of sigma plus it is not equal to 0 if sigma is greater than 1.
Что при части S больше единицы, z не входит.
This is from functional equation.
No.
No, I think we know everything a lot for S greater for sigma greater than 1, and functional equation is used to know something about sigma less than 0.
Это можно понять исключительно из изначального определения этой функции?
Ну,
Смотря что считать изначального
Ну,
определения.
ряд.
Ну, можно точно понять еще про этот ряд.
Сумма n минус s.
Do you know what is zeta to the power minus 1? Yes? We write it a formula that on the first seminar.
Функция Мёбиуса. Функция Мёбиуса делить на...
Ага, sum of Möbius function over n plus. If zeta has 0, then this has a pole. But this series, of course, is absolutely convergent. Our way to do it is to look at earlier product. Okay, and what about this?
We should probably use the functional equation.
Yes. Yes, let's analyze. Zeta of S is 2s by s minus 1 ps 1 minus s for s less than 0. What's this? Of course, these two terms are entire functions. Yes. What about gamma? Do you know, does gamma function has any zeros? Who knows?
I know that it has poles in
Yes,
minus
it
1,
has
minus 2,
poles.
minus
And
3.
what about zeros? Actually, look at this memo.
I don't think it does.
Look at formula for gamma to the power minus 1 in your papers. You see, actually, gamma to the power minus 1 is an entire function, целая функция. It doesn't have any poles. So gamma doesn't have any zeros.
I say a very stupid argument why gamma function does not have any zeros. Suppose gamma of 1 minus s is equal to 0. Then gamma of s should be equal to infinity, right? Because we have reflection formula.
Yeah, so it's a pole, but
So if you multiply gamma of 1 minus s by gamma of s, you get pi over sine pi s. So if s is not an integer, then gamma of s multiplied by gamma of 1 minus s should be finite. So if gamma of 1 minus s is equal to 0, then gamma of s is equal to infinity.
С какой формулы стартовали?
Гамма от s умножить на гамма от 1 минус s это π поделить на синус ps. Поэтому если s не целая, а гамма от 1 минус s это 0, то гамма от s это бесконечность. Ну и все.
yeah, but if s is an integer, you have to have another argument again.
Что?
If s is an integer, you have
А
to.
если s целая, то оно либо отрицательное, и тогда там полюс,
Yes.
либо положительное, и тогда там факториал.
Well, okay, yes.
Ну, там разные можно стили.
Стирлинга.
Ну, у нас стилинг получается. Стилинг. Ну, окей. This is not 0, this is not 0. Z of 1 minus s, we know that it is not 0. So only sign can be 0. And for which s it is 0, for
When is side by s over 2 0?
When s is even.
Yes, s is
No.
minus. Yes, and it's actually we saw it successfully. Okay. Next, we want to prove that zeta has no zeros here from 0 to 1 and hence in some origin. Let us consider such sum.
So once again, all the zeros outside the critical strip are negative even integers.
Yes, excluding 0. These are zeros.
Trivial.
Now, I want to say that you can compute such sum. So we have 5 minutes. We have such sum. What is it in terms of zeta?
Zeta.
So it's minus 1 plus 1 over 2s minus s minus. I want to write it in terms of zeta.
Any ideas? Any suggestions?
It has to be simple.
What if we multiply zeta of s by?
Wait.
Okay.
Why do you need to spoil everything so far? Maybe we could do it different. What if we write the same sum as zeta function, but only over odd integers? So we see that this series differs from zeta function by having minuses in front of. Можно и такой подход, да.
А, ну сложим с z от s и
Вот
получим.
такая штука чему равна?
Зета функция умножить на 2 в степени минус.
Угу.
Now we can compute this.
Главное, там первый курс приехал.
Ну вы что думаете, 19 век?
Для 19 больше, чем 1.
В первом веке не было интернета.
Архимед.
Какие-то древние греки что-то писали. Потом записывали, потом перевели.
Okay, in this exercise we have minus 1. It is not
It is crucial to mess up the signs even number of times.
Можно представить это как z функция от s минус 2 умноженное вот на вот это 2 в степени минус s.
Конечно.
So this will be 1 minus 2 minus s, zeta of s, yes.
By the way, now we can notice something.
Yes.
This function has no pole at s equals 1, right?
Because here
the pole of zeta
for
is
s,
cancelled out.
yes. And when this sum converges, for which?
Это вот там зета функция или ее
Z.
z.
Z, да?
какой тонкий подход на нашему почерку.
Я просто помню то, что я в начале еще занятия я что-то видел там, тут эта функция столько силы.
Там пока не скажете, там не будет понятно.
Я еще совсем не понял, что произошло. Когда в каком-то месте как будто бы одна из этих функций стала кси-функцией.
Okay, we have such sum here over n 2n minus 1 minus s minus 2n
Есть те, кто русский не понимает.
minus s.
Замечательно, кто русский не понимает.
Спросите по-английски.
Это шутка была.
Вообще вот.
Ну ладно.
I don't understand why can you change the order of the summation. No.
Where?
This is the formal
Yeah.
identity of the Dirichlet series, right?
There is no change of order of summation. Where it is?
This is a formal identity of the Dirichlet series, once again. You have Dirichlet series on the left, it is a dimension function.
You
on
mean
the
why we
side.
can change? Because we this formula we prove for real part of s greater than 1. Okay?
Yes, so
In this
such
case,
an
it's-
operation is highly illegal when you have divergent series. You know about it, right?
Yes, and now I want to say that this sum, now we somehow deleted our pole at 1, and now our sum, it converges for real part of s greater than 0.
What are we proving?
We prove that we want to prove that such sum converges in this range. Уже конец, да?
Let's prove it when s is between 0 and 1.
Yes.
For real values.
Yes. Otherwise, you just consider such difference, and its Taylor series will cancel somehow, and it will. Yes. Yes. Let us assume now, for now, that s is real. When it certainly converges, yes. And to what?
If s is real, then this series here is convergent, right? Because it's one half of a telescopic series.
What is the telescopic series?
I mean series of the form an minus an plus 1, some an going to 0.
We have such series, and these sums, they are all positive, and they decrease. So this will be this will equal than 1.
And greater than 0,
Yes, and greater than 0.
right?
Безо всяких интегралов Абелей.
Yes, and
Вообще без ничего.
And so we see that, first of all, we see that z of s it changes as sign, знак, at 1, of course it should change. And it has no zeros here.
So, of course, zeta function is real when s is real. But it is positive when real part of s is greater than 1. Then it's negative when real part of s is between 1 and 0. And then it also changes sign at -2, then at -4, and so on.
Yes.
Because the zeros are simple.
Yes, maybe it's not so clear why it converges for real s bigger than 0. You need to.
What? It is absolutely obvious why this converges. Let me show you. Not you, but for them. like to prove that this series converges.
Нет, при S комплексном смысле.
If X
Ну да, мы же
converges,
хотим
then-
аналитическое что-то продолжить.
then it is less obvious that
Ну
this
да.
converges, but still, if n is large, then double n minus 1 to the minus s is equal to n to the minus double n to the minus s, 1 minus 1 over double s to the minus s, which is equal to 2n to the minus s plus big O of big O dependent on s, of course, of n to the minus sigma minus 1. Correct?
Всё сходится. Ага.
This is due to Taylor expansion. And then this thing cancels out, and those things are absolutely convergent. That's it.
Окей. Окей, спасибо.
When do we have to see
Правильно я уловил, что единица 0 в этой функции?
Вот у этой?
Нету ни нуля.
Нет, потому что у z это полюс, а у этой 0.
Они сокращают.
И получается две двойки. Вот из этой двойки.
we have lecture notes? When do we have lecture notes?
Когда, ну, во-первых, потому что известный факт, изменился на второе а во-вторых, ну, у этой вычет 1, а у этой, если 0, посчитать само другое.
Просто есть выкрутый.
Ну, должен
Сейчас,
быть.
сейчас. У этой вычет 1, а у этой что?
А у этой 0 с каким коэффициентом? Ну, там, с минус 1 умножить на что? Я думаю, там это должно быть.
If real part is greater than 1, then you can
Потому что сумма должна быть.
change some of the
Хотя ну, так
however you want, and everything works, right? And then it works by analytic communication.